So how's it going with your homework? Is it going well? Is there anyone who have done already or finished it, the homework? Okay, maybe a few students. So even though the homework is to write some programming kind of code, but you will find it mostly deriving those gradient equations, especially in the vectorized form. Okay, so let me continue a little bit about this vectorized form and its gradient. So we learned at the end of the last lecture, we learned that this vectorized form of a computational graph is nothing but just a compact form of just a computational graph, which is composed of all the scalar components, right? And then it's just a rearrangement of our scalar variables or parameters into a vector or matrix form, right? And then now I think you guys are already studied the derivation of dx being equal to dy times W transpose, right? So it was in the video that I asked you to watch, right? Okay, and and one thing that I want to note here is that this guy is really, it's not really dx. Its meaning is df over dx, right? So it's not like dy over dx and this particular denominator or numerator. It's really, the numerator is fixed as our final loss function f, right? And then it means the partial derivative of that common function of our loss function with respect to a different variable. Here the variable is x, and this guy is df over dy. Okay, so okay, so I think you guys understand this equation, and then now so in this equation we in this linear layer we have w and x, and we have y here, right? So this is just a simple vectorized form of a fully connected layer where y is w times x, right? And then now we have to obtain the partial derivative with respect to each of our input variable. So we understood this part of dx being equal to w transpose dy, but let's derive this part of dw over df. Okay, so in this case just like the video that in the previous video, let's just think of a different representation of this computational graph into this form. We have 3 input nodes and 2 output nodes, and this is y1 and y2 and x1, x2 and x3, and then we have w, which is representing this fully connected layer. Okay, and then so this vector output is represented as w times x, right? And then let's enumerate each elements in our W as W11, W12, W13, W21, W22, W23. Okay. Okay, and then we want to obtain this guy, right? df over dw, and then that part is still the same, I mean having the same shape of 2 by 3 matrix, right? And then each element in this part will be dw11, dw12, dw13, and so on, right? Let me just finish it. Okay, and then now let's just fill that out, element by element. So what is this gradient with respect to W11? So in this case, where is W11? So if you imagine we have W11 here, right? And then it is actually multiplied and then added together to form Y1, right? Okay, so this Y1, I mean, yeah, this W11 and X1 and multiplied, and W12 and X2, and these are multiplied, 13 and X3. Sorry for bad handwriting, but you get the idea. And we get the addition at the end, right? And then if we reach the gradient arrived at this point, and the gradient is dy1, right? Because this guy is our output node of our interest. And then we have an add gate here, so gradient will be multiplied, I mean duplicated, right? And so the gradient will be all the same, right? And then what about this multiplication for the gradient kind of conversion? It is a gradient switcher, right? So we want to have the gradient with respect to W11. So we have to multiply this guy with X1, right? Okay, so this guy is dy1 times X1, right? And then what about the gradient with respect to W12? It is similarly obtained as this guy, right? So far so good, right? So does it make sense, right? 표정들이 안 좋은데. 이해 가죠? 예? 안 가는 사람? 뭐 되게 쉬운 건데 그리고 또 되게 중요한 거라서. Okay. Okay. So we got this, right? So this is our gradient with respect to this whole matrix W, right? Or in short, this guy, right? Okay, so I need to separate it. Okay, and then let me just rewrite it as a outer product form. And how? So as you can see, each column will all have the elements as dy1 and dy2, right? And all rows will have x1, x2, and x3. And so it can be factorized into this form, dy1 and dy2 as a column vector, and x1, x2, x3, right? So yeah, this was coming, yeah, I mean, this was part of 4 different perspectives of matrix multiplication, right? So, yeah, suppose we perform this matrix multiplication where we have 2 columns and 2 rows on the left and right respectively, and then we know this times this, right, and this times this. Those 2 outer products are added together, right? And so this guy is x1 and y x2, and this row is y1 transpose, and this is a y2 transpose, and x1 and y1 transpose plus x2 and y2 transpose, right? So this was fourth perspective of, yeah, understanding matrix multiplication. I mean, if you don't have much idea about this, and then please review what I asked you to watch in terms of matrix multiplication. Okay, so in this case, this is nothing but a special case where we have just a 1 column and 1 row, and being able to represent this whole matrix as a single sum of outer product, right? And so if you just do this computations mechanically, and then you should be able to, you should be able to see this one being true, right? Okay. So this guy is dy times x transpose, right? So this is our conclusion. I mean, the derivation of our derivative of this matrix W in the fully connected layer in this vectorized form. Okay. Okay, and then let me So this is not the end. I mean, in order to properly solve our homework, we need a 1 step further from this, which is kind of a batch version. I mean, the vectorized version of using our batch instead of just a single column of an x and y. So, when involving our batch, and then we consider within our mini batch, we have a multiple x values and also y, multiple x vectors and y vectors as well, right? Okay, so suppose we obtain, so given the first input vector 1, 2, 3, and then suppose we obtain the output as 4, 5, and then as a second data item, which is maybe 6, 7, 8 as another input vector, and then we obtained maybe 9 and 10 as another output vector. Okay, and then our vectorized form will have this form: 1, 2, 3, and 4, 5 as an output vector, right? And then in terms of the next input vector, we concatenate it column-wise over here. And then 6, 7, 8. And then what is the corresponding output? The output will be placed over here, 9 and 10, right? So this one is actually, this one can be viewed as the another perspectives of matrix multiplication. So if you guys remember another type of a matrix multiplication, and then it can be viewed as a column combination. So we have a 3 column on the left, right? And then what are these? So what's the role of them? So these will be working as a linear combination coefficient for each of these three columns, right? And then we linearly combine them together, right? So yeah, maybe, yeah, let me just give an example of maybe 1, 1, -1 and 0, and 0 and 1. And then this 4, 5, I mean, it's a hypothetical example, but this 1, 1 and -1 and 0 and 0 and 1 and 1 times and 2 times and 3 times, and then we add them together, right? So this column combination will form the first column of an output matrix, right? And then what about the second column on the right? So that will work as a linear, the new linear combination coefficient that will replace this guy, right? So 6 and 7 and 8, but we use the same columns, right? I mean, common set of columns provided over here on the left, right? But using different linear combination coefficient, and that will form the second column of our output, right? Okay, so this was a column combination view of a matrix multiplication. Okay, and then let's go back to this derivative with respect to our matrix W. Okay, and then let me just write this guy as x1 and x2 because they are two different data items that we have, right? So those two will form our batch, right? And then this guy is y1, the first output, and the second output, right? Okay, and then so we have W here. Okay, so this whole equation, I mean this single equation, yeah, is equivalent to like W and x1 and the y1 and W and x2 and y2, right? So this is just the same thing that I just explained, because using the same matrix W, using the first column, we will form the first column, and using the second column, we form the second column. So they can be entirely separated, from each other. Okay, so that way we can easily write them in this form, right? Okay, and then if you imagine the backpropagation and like generating the loss and then causing some gradient and then doing the backpropagation, and then loss will be incurred from each of our data point, right? So this is the first data item, and then this is the second data item, and each of them will have their own loss value and then their own gradient values, right? And so at this point of on y, we will have its own gradient, which is our d of y1 and d of y2. And these are actually a vector, right? These are actually a vector. And also this is another vector, which is two-dimensional vector. I mean, again, we are dealing with this fully connected layer like this, right? And when putting the first data item, and then we will do the forward pass, and then do the back propagation, and then we will have the gradient for this, for the first data item, right? And then, okay, so what about the gradient with respect to W? So W will have also its own gradient coming from the first data item. And what was the equation? That equation is this, right? So this was the gradient, I mean the derivation of the gradient with respect to W, right? When considering only a single data item, right? Okay, so we have the gradient, caused by the first data item and the second data item, right? Right? And then how should we combine those two gradients? I mean, so those two different gradients caused by the first and the second data items, and they are causing the gradient with to the same guy, I mean same W matrix, right? So if you imagine, okay, so this is a little kind of messy but clearer kind of clearer form of our computational graph, right? And then this was our first feature, but it's coming from, I mean, it's from the first data item, right? And then what about the second data item? So the first feature of the first data item and the first feature of the second data item can be viewed as different data items and thus different nodes in our computational graph, right? So yeah, I mean, it seems that you guys don't understand properly, so I get to explain more and more details. Yeah, but I mean, suppose we have two data items. I mean, let's go back to really simple, a linear regression, where we have our model is just y equals ax, and the first data item is a 1, and the target value is 2 and maybe 5. Okay, so in this case, what is our loss function? A times 1 minus 2 squared, a times 2 minus 5 squared, right? So this is our least square loss, right? And then how do we represent it as a computational graph? A, right? And this is the first data item's feature, and this is the second data item's feature, right? And thus x1 and x2, right? And then multiply together and maybe y1, and take the difference between them and then take the square of them. Okay. And also this A is also connected with the second data item, right? But A is the common node, but x1 and x2 are two different nodes because they are two different data items, right? And thus y2 and then they are finally added together. So this is our final loss function that represents this function, right? Okay, so my point here was this parameter A is connected commonly to the first data item and the second data item, right? And thus this A has actually branch, right? Branching into two different paths, right? And when a single node is branching out, and then how do we deal with their gradient coming from this flow and this flow? They are added together, right? So that was multivariable chain rule, right? So all these previously learned stuffs are connected together, right? So there is no magic at all. So that's the reason why you really need a solid background from the beginning. Okay, I mean the fundamental should be strong. Okay, so back to this part. this W, which is our vector node, is commonly connected with the first data item and the second data item, and then each of them will cause or generate this gradient, and they will be what? Added together, right? Because our loss function will involve the summation, I mean the summing of all the losses from each data item, right? So far so good? Okay, so we can then rewrite this dw as simply the sum of these two. Okay, and then we were able to factorize this out into dy1 and x1 transpose, right? And dy2 and x2 transpose, right? So far so good, right? And then how can we rearrange them? We can further rearrange or rewrite it into this form. So this is really this sum of outer product, right? So here each of them is just a product of column and row, right? Two vectors as an outer product, and they are added together, and then we can rewrite it into a single matrix multiplication form. And how? Yep. So this guy comes here, and this guy comes here. Okay, and then this guy is over here, and this guy is over here. So this is just a rearrangement with respect to columns and the rows, right? Okay, so our final conclusion is dy and dx transpose, where this y has the columns of the gradient coming from each data items like this, and then the matrix x, so we shouldn't have d over here. So x is just a matrix whose rows are each data item's input vector, right? So this is our final vectorized form when considering the mini batch or the data items as also the vector to vectorize. Any questions about it? 다 이해 간 거예요? Okay, so if you don't understand, I can explain it with no problem. I mean, explain it again. So feel free to just ask anytime. Okay. So it's almost always true that you are not alone when you don't understand something. Okay. Okay, then so that's probably it for the backpropagation. And one big thing that you have to understand while doing the homework is the backpropagation, derivation of the backpropagation for the softmax layer. So the softmax layer. Okay. So yeah. Yeah, maybe when we have 4 input nodes and then the 3 nodes corresponding to our each of our class. Maybe it's dog and cat and maybe sheep. And you guys know how the softmax works, right? And then suppose, yeah, so this value is 2 and 7 and -1, and then you know how to convert them or transform them into a softmax layer output, right? And then, which is some probability value, and that suppose that probability value was maybe 10% and 85% and 0.5%. Okay. Okay, and when doing when our loss is softmax loss or cross entropy loss, and that image, I mean the input has a ground truth as maybe cat. Okay, so in this case, what is the gradient at this vector? Okay, what is the gradient at this vector? So this output, I mean, first of all, what is the loss value? Loss is negative log what? Point. What is the loss? It is our loss, right? Because currently the ground truth node has the output of 85% from our forward propagation, right? Okay, and then just if you derive the gradient with respect to each of our softmax probability values, and then what is the gradient? I mean, this, suppose this, let's call it as a vector y, okay? And then what is dy? What is dy? So just like the fully connected layer that we saw, okay? So just like we have some activation over here, right? And then during the backpropagation, we will have some gradient value arriving at those nodes, right? From the backpropagation, right? And what is that gradient arriving at this vector y? Okay, so if if you guys did a homework and then finishes the derivation of it, and then it is simply the difference between this guy and this guy. So we basically subtract this 1-up vector, I mean this output vector, from the ground truth vector. Okay, so 0. No, sorry. This vector minus ground truth vector, 1-up vector, right? And so this is a 0.1 and -15 and 0.05, because we have a corresponding ground truth value as 0, and so 0.1 minus 0 will be 0.1, right? And 0.85 minus 1 will be -0.15, right? And then how can we understand this gradient value? Okay? How can we understand this gradient value? So this is our dy, and then so first of all, can we directly do the gradient descent update on this y? Is it possible? So let me ask again. So in this case, can we directly update this y using the gradient descent update? So my expected answer is no. So because this y is not our parameter, so they are just a neural net, intermediate output in our neural net, right? Our parameter that we can directly update is involved over here, right? And also but on the other hand, in this softmax layer, I'm not gonna write the softmax equation, but in the case of softmax function, there is no trainable parameters. It's just a fixed function, right? And so from this value to this value, so there is no parameters involved, and also these are not our parameter that we can directly update, right? Okay, but let's just imagine we can update these values directly. Okay, and what does that mean? So if we could do the gradient descent update, and then this value 0.1 should be updated in the following manner. So suppose our step size is a point, maybe 2 times 0.1, right? Because this is a current value, and this is step size, and this is our gradient, right? So what does it say? So currently, the probability assigned to the dog class is 10%, right? But that 10% should be decreased or increased? Decreased because of this gradient descent update, right? And how much? In proportion to its original probability value, right? So if that probability was like 0.4, which is relatively high, and then it will have the gradient which is proportional to the current value, right? And so it will be more suppressed, right? It's like, so do you guys remember kind of similar updating? Similar updating pattern. Okay, bonus point. So if you can answer this question, and then I give you the bonus point. So it was we discussed it very early in our lecture, maybe in the first week or so. So when do we have such amount of the gradient which is proportional to the original value? So that was like this kind of regularization thing, right? If we do the L2 regularization, right? And then suppose we have AX plus B as our linear combination, linear regression formula. And then our L2 regularization will be some regularization parameter, maybe gamma, and alpha squared, A squared and B squared, right? And then its gradient will be like 2A, which is proportional to the original value of an A, right? The current value of an A. So that will be our gradient. It is proportional to the original value or the current value. So if it's a larger value, and then it will be more suppressed. If it is a really small value, close to 0, and then it will be really suppressed with the small amount, right? So this kind of a gradient updating pattern is also just to give you some So we will study in the later chapter of this CS231N, but I'm gonna just give you Oops. What? So this is a technique called the deep dream, which is imposing what the deep learning would imagine or would dream given a particular image. Okay, so this is just a grocery shop's video or a sequence of images of grocery shops, and then deep learning is actually dreaming that there are some dogs or cats somewhere in this grocery store. Okay, so how do you achieve this kind of algorithm? So this is nothing but just creating artificially the gradient, which is proportional to our input value. Okay. Okay. So so back to this example. Okay, back to this example. Even though we cannot directly update y's, or it doesn't make sense to even consider or think of updating y's, but that deep dream is actually making, that actually changes our kind of thoughts, and then it kind of imposes that kind of direct updates on typically those nodes that are typically impossible to update. Okay, but anyways, okay, so you guys get the idea or the intuition about this gradient caused by our softmax. Okay, and then also about this node of 0.85, and then we do not subtract 0 because that is really our ground truth node, and thus we subtract it. We subtract 1 from it, right? And thus this is our gradient, right? So this is just a side note, but so I was initially confused, or I didn't initially memorize the gradient of this softmax between like which one to subtract from the other, right? So you guys remember I was just confused, right, for a moment, right? And then when I wrote this gradient with the flipped sign, and then it didn't make sense when imagining their gradient, or which value do these values want to be updated as? Okay. But anyways, so this guy, negative 0.15, is actually reflecting our intent to make this value larger. Okay, so in the case of imagining kind of a gradient descent update, and then it will be like this. So it will be acting as a positive value, right? And so we want that value to be higher, close to 1. Okay, but if it is a really close, okay, if it is a really close as maybe 0.99, and then correspondingly the gradient will become much small, right? Because the difference between these two will be really small, right? And so the gradient will be small, and thus our network will not try too much to increase that value. Any questions so far? Okay, so related to this issue or this perspective, back to this example of fully connected layer. So suppose we obtained dy, and then why do we need to compute both of dw and dx, or maybe dx as so this is a matrix version, or small x is just a vector version of an x. But why do we need to compute both of them, right? So in the case of dw, how do we use them? So once we obtain the dw, and then how do we use them? So they will be used to directly update our current w, right? Right? Suppose our current w was maybe 1, 0, 1, 2, 3, negative 1. Suppose this one is our current W, and then suppose we obtained dW as some matrix. And then we just multiply the step size and then subtract it from this the current matrix. So that's how we update our W, because W is our parameter that we directly update, right? But what about dx? Should we, do we need to compute dx at all? So if it was our initial input node, and then we wouldn't need to compute the gradient with respect to x, but in general, this fully connected layer can be placed in the middle of our entire network, right? And then what is our x? So x will be the output of the previous layer, right? And so we need to provide dy to that previous layer, or the gradient of the output of the previous layer, right? So dx computed in this step is used as the gradient of the output to the previous layer. So we need to compute both of them in general, in almost all cases. Any questions so far? Okay, so probably that's it for the backpropagation. Okay, so now this is probably the hardest part, or most difficult part when studying the deep learning. So once you mastered how this backpropagation works, and then the rest of the stories in deep learning, yeah, it's relatively easy, I think. So okay, so let's move on to the next chapter of the convolutional neural nets. Okay, so let me address this question about the inner product computation, mainly used in the CNN operation. So convolution is basically an inner product computation, right? And the inner product computation, intuitive understanding of this inner product computation is to compute the similarity between the two vectors by using the inner product, okay? So I'm not sure if I explained it or not, but so you guys know the cosine similarity, right? To measure or evaluate the differences or similarities between the two vectors, and this cosine similarity is defined as this guy, the inner product between the two vectors, and right. So if our vector was maybe 2, 1, and maybe 1, 3, and then the inner product is what? 1 times 2 and 3 times 1, right? So that's the inner product, right? And then in the case of a cosine similarity, we normalize them based on their lengths, right? Okay, so Okay, so this is our cosine similarity, and thus we can even obtain the angle over here, which is what? 45 degree, right? Okay, so the main idea of the cosine similarity is that if the two, the angle between the two vectors are small, and then we treat those two vectors being similar to each other, right? So that's the main idea of this cosine similarity. So that's a very basic thing, right? And here, in many cases in deep learning or many other applications of machine learning, so we sometimes just omit this length normalization when computing the similarity between the two vectors. Okay, so in many cases, just computing the inner product can work as the similarity measure. Okay, so what's the difference when using the inner product as a similarity when compared to cosine similarity measure? So yeah, if we have really long vector, and then even if that vector has a large angle with the other vector, and then if that vector length is really large, and then it will mostly have large inner product similarity with the other vectors, right? So it's like making this a similarity game unfair, because we are giving, like, regardless of whatever the other vector is, if one particular vector has a really large length, long length, and then it will mostly have a large similarity with the whatever the other vector is, right? But that is okay, right? So that is okay, because our neural net will handle this issue through our backpropagation. So if we use this imperfect inner product measure as our, imperfect similarity measure, okay? If we just use an inner product, then that should be okay. Through our backpropagation, those imperfect similarity measure will be kind of considered and adjusted through like optimizing other parameters, okay? And also there are some cases where this inner product similarity makes sense as well. So suppose a particular vector is really having a large similarity with most of the other vectors. Okay, so if you remember the role of the bias in our softmax layer, or maybe softmax classifier, right? So if we add or if we assign more bias or larger bias value, and then it's like we are giving more probability even before looking at the input image. So we are giving larger probability to that class, right? So that way we may want to give some bias or some more probability or similarity to a particular vectors, right? So that way this inner product will work as a similarity measure just okay. So, and also this cosine similarity, the main kind of issue of this cosine similarity is that this length computation is sometimes quite burdensome, okay? So this inner product is really, really simple, and that can be highly optimized or highly parallelized through our GPU, okay? Like NVIDIA's 1080 Ti or 2080 Ti, which is recently available. And all these GPU computations are nothing but just making inner product parallel, okay? Or this inner product in general can be represented as a matrix multiplication. For example, if you saw this matrix W and maybe X, maybe we have more number of an X, okay? So this is our X, which is our batch, which is in 3-dimensional, and our batch size is 5. Okay, so in this case, it's all about the inner product, because so we have an inner product over here, and also inner product over here, and over here, and so on. So how many inner product do we have here? 10 inner product between two three-dimensional vectors, right? So it's all about the inner product, and GPU is nothing but the device that does this inner product computation highly parallel. Okay, so that's the introductory kind of justification of the use of the inner product in the case of a convolutional neural nets. And then convolutional neural net is also a the inner product. Let's see. Okay, so you guys know how this inner product works in the case of convolutional neural net, right? So suppose we have maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, and our filter is maybe 1, 1, 1, and 0, 0, 0, 0, 0, 0. Okay, and then if we just compute the activation on that particular position, and then the inner product, I mean the output, activation output will be 15, right? Because we are doing 9-dimensional inner product, right? And 9-dimensional inner product is repetitively done by just moving one by one our filters, right? Horizontally and vertically, right? And then, the reason why I mentioned or I discussed about the inner product as a similarity measure is because this convolution can be viewed as just computing this similarity, okay? Similarity with this fixed filter, okay? By just moving it around in our image horizontally or vertically, right? So we just compute the similarity at each different position and evaluate where is the position that has the highest similarity, kind of thing. Okay. So that way, it is also when computing this output of this convolution, and we sometimes call it as activation map, right? So this activation map is typically referring to like the input or the output matrix between the convolutional neural net or convolution layers, right? But what is the meaning of this activation? So activation is really like how similar the particular position is with the given filter, okay? So it's like detecting our patterns that we look at, okay? And also, back to this inner product or inner product similarity. We usually treat, I mean, in the context of a convolutional neural nets, we usually treat the, given our filter as like this, and then you can just you can consider this as the pattern kind of extractor that has this kind of shape, right? So this is the most basic part of this convolutional neural net, but at the same time it's a little, kind of difficult to explain, or a little bit tricky. I mean, most basic things are the most tricky thing to explain, but so suppose your filter has like this, and then in some high dimensional space or maybe 9-dimensional space, right? And then this filter will have the fixed direction and maybe length, right? Okay. And then suppose we have a really big image, okay? And then we move or we match this filter at this position or at this position and so on. And then you can imagine each different places we will obtain different 9-dimensional vector, right? And that 9-dimensional vector will be placed over here or over here or over here, over here, and so on, right? And then if we just compute the inner product with this guy and this guy, and then we consider the length of these two, and then also the angle, right? And then now let's imagine, I mean, this is just a one kind of simple approximation that we impose, but yeah, stochastically or on average, at each different positions, the 9-dimensional vector length coming from our image has the same length. Okay. Again, our assumption is at each different position that we match our filters with in our image, suppose each of different image regions has approximately the same vector length. Okay, and in that case, all these red vectors will be treated as having the same length. Okay, and then suppose that length has maybe radius of 5, and then those vectors will be on this circumference of our circle, right? I mean, this is just one kind of assumption, but yeah, let's just make that assumption, and then now inner product similarity is ending up with like similar, really similar to cosine similarity. That, I mean, in order to have a maximum possible similarity value, and then the angle should be minimized, right? And so, given this filter vector, I mean, given this vector represented as our filter, and then when do we have a maximum inner product similarity? It will have the same direction, okay, same direction. And then that same direction can also be further simplified, that suppose we have the same length as the filter, okay, the same length as the filter vector, and then our maximum possible similarity is obtained from the same vector as our filters, right? So my point is that if our filter, if we are given this particular filter, and then we are looking for, or the maximum possible similarity is obtained when we have the patch as this exact shape among our big image. Okay, so I mean, this is a kind of so as we imposed, there are several unjustified assumptions involved here, but you can just have this kind of intuitive idea that given this particular filter coefficient, we are looking for that exact same pattern to maximize the similarity. Okay, and if the similarity is not maximal, and then maybe that filter, I mean, that region may have like this kind of pattern, which is not exactly the same, but almost the same. In this case, the similarity will be non-maximal value, but it is relatively high, right? Any questions so far? So let me give some example. Okay, so suppose these are, I should have started with this simple example, but suppose we prepared for these 3 different filter patterns, right? And then suppose this is our original image, where this black ones representing -1, and white ones is representing 1. Okay, and then if we just move this filter around, let's see. Okay, so at this particular position, okay, at this particular position, we will have a perfect match, right? So in this case, if this region, this region has exact same values as that filter pattern that we are looking for, and then in that case, the inner product between this filter and that region will have really the maximum similarity value, right? Even though we we computed the inner product and then we just simply divided it with the number of dimensions, but that's just some additional things. Okay, so if we just apply it into different region that doesn't exactly have the same pattern, and then the activation will be smaller than the maximal activation of 1. Okay, so this is our final activation map. Okay, so that means when using this filter at this position where this part is centered at this position, and then we have over here we have a maximum pattern matching or maximum similarity that we can get, right? And so we obtain the maximum similarity over here and over here, which is corresponding to those two positions, right? And then over here and over here. So in that case, we obtain, we apply this part, and that will also have the exact match, right? And all the other parts, they will not have the maximum similarity value, right? Because the patterns are not exactly matching, right? So this guy is called the activation map, which means how much activated a particular region in our image by matching it with our given filter. Okay. So I hope it gave some intuitive understanding or explanation about the inner product, the notion of the inner product used for the convolution. And then, is there any other methods or other ways to compute the activation output? I have no idea. Yeah. Is there any other ways that you guys seen?
I just have a question on the previous part.
Okay.
You said that you can learn the normalization part of vector variation. But how can you account for different brightness areas in the picture and put the same convolution over every pixel?
You mean in the case of a bright region, and then we will get mostly high activation? Is it? Yeah, right.
Or the reverse.
What's that?
Or the reverse.
Yeah. In the opposite case, you mean? Dark regions will have mostly low activation, right? Okay, so in this case, so that is related to this assumption, or here we assume that each different locations will have the same vector length, right? So in mostly like bright regions, and then it will have a relatively large length than the other regions, right? So in that case, regardless of whatever particular filter shape that we match or compare, it will mostly have the high activation value, because from the inner product, I mean, that region itself has really large lengths of the vector, right? Yep, so that is the limitation in general of the inner product, which is used as a similarity measure, right? But that is also considered, like in this particular case. So for those regions that we impose our patterns, if we can freely we can set their values as positive values, but at the same time, for those regions that we shouldn't we should not match, we can assign the negative coefficient, right? So if the regions are all bright, and then we can approximately have all the ones in all these 9 different locations, right? So in that case, the activation value will be negative values, right? So we can kind of manipulate our filter coefficients so that we can kind of penalize all the bright regions or the dark regions and so on. Okay. Any other questions? Okay, so other than the inner products, to my knowledge, I don't have any idea. So typically, I mean, inner product is a really simple operation, right? And so we usually define our convolution as really this simple operation. And then if we want to make our model more complicated or more capable, and then we typically we combine them in many different ways, like stacking them into multiple layers, and also in the case of within a single convolutional layers, we usually have the same number of, same filter size, right? So in the case of okay. So this is representing one single convolution layer. How many convolution filters do we have here? So this was one of our quiz problem, right? So if we have output activation channel that has the depth of 6, and then it means our filters, the number of filters is 6, right? And then also, let me also check the other problem in our quiz. So given this input activation map, what's the depth of our convolution filter? 3, right? So somewhere in the other slides, so there was a kind of a note or mentioning that we always fix the full the depth of our convolution filter with the full depth of the input activation map, right? And so if we are given a input channel S3, and then each of our filter in our convolution layer will have the depth of 3, right? But anyways, if we have 6 different convolution filters within a single convolution layer, and then we obtain 6 different activation map, thus resulting in like 28 by 28 by 6 as our final activation map, right? And then here, you guys understand this stride, right? And also padding size, and also convolution filter size, right? And then within a single convolution layer, you can just manipulate them, or these are the hyperparameters that you have to choose, right? And then can we, is it possible to make this convolution layer more interesting so that we have a different size of filters within a single layer, or different stride size or padding size as well? So you can certainly define such more interesting convolution layers as well, right? So in that case, suppose among the 6 convolution filters, 2 of them are 3 by 3, okay, 3 by 3, and maybe 2 of the other filters will have 5 by 5 convolutions or filter size, and of course the depth should be 3, right? So in that case, what is the problem in this case? What is the issue? Output sizing. Okay, yeah. So if we don't allow any paddings over here, and then you guys know that activation map in terms of a width and height will be decreased when using a larger filter size, right? Larger filter size. Okay, so that is the issue, right? And so each activation map over here, which is a one thin matrix, will have a different horizontal or vertical size, right? And then how can we match them? Can we match them? I mean, how can we match them? We can simply change the padding size for each different filter size, right? So usually in the case of, so that was another quiz problem, but in the case of 3 by 3 convolution filters, and then how many paddings do we have in order to have the same width and height between input and output activation map? How many? 1? Or what about 3 by 3? It's 2, right? So for different filter size, we can definitely use different padding size, right? And also, this is about the basics of the convolution, but you can think of when thinking of the output activation map, and then suppose we apply the 3 by 3 filters, and then for one activation map, you can always think of it. You can always think of matching it with the center position in the matching regions. So if we just apply our filter at that position, and then we will obtain some activation map as a scalar value at that particular position. And this value, you can think of this value belonging to this guy, okay, this single pixel, okay. So this activation value is belonging to this single pixel in our input, okay. So if we just align this the center pixel in this manner, and then this should be one of our input pixel in our image, and thus it can be over here and over here and over here, right? So if this guy was a center pixel, and then we need still one more pixels on the right, and so we need one more kind of line on the right vertically, right? So back to this guy. So we have this filter to match among different locations, and then I mentioned that the center pixel will have the activation as 0.77, and this center pixel will have the activation as 0.1, right? So that way, even though the convolution, one convolution operation will involve multiple pixels within that filter size. But you can always map this kind of one-to-one mapping between these pixels between input and output images. So you can think of it that way to help you understand this better in terms of the padding size needed and things like that. Okay. Any questions so far? Okay, so yeah, so we now understand that we have no problem of using different filter sizes within a single layer, and then in order to make the same width and height in terms of an activation map size, we can adjust the padding size accordingly. Yeah, but sometimes so I need to explain the application of this convolutional neural nets in the case of a text data. Let's see. Let me see if I can explain it quite quickly. So this is one really famous famous example where you can where the convolutional neural net was applied to the text classification. Okay, so image data is not the only application that CNN is applied. It's actually applied to many other data, such as time series data or this text data. Yeah, so this is one example of the text data, and then this is the so in this case, the text data is what is width or height? So in the case of text data, it is just a one-dimensional data. Okay, unlike the images that has the two dimensions of width and height. But in the case of text, we have this one dimensions, right? Which is the order of words that appears in our sentence. And then here, let's suppose the task is to classify the given sentence as being positive or negative sentence. I mean sentiment. Okay, so like this movie is really awesome, and then it should be classified as positive sentiment, or this movie is awful, and then it should be classified as negative one. And then so this one is actually our each pixel. Okay, so these are each pixel, just like our 2D images, and each pixel is originally represented as how many dimensional vectors? Each pixel is usually represented as 3-dimensional vectors in terms of RGB values, right? So already one particular position, that position is represented as a vector, right? In the case of an image. And also in the case of text, we have a way to represent each word, which is corresponding to our pixel, as a vector, right? As a fixed dimensional vector. And that fixed dimension is 5, okay? And then now this is a one-dimensional data, and thus if we imagine the convolution layer over here, and then this is our depth. This is our depth or channel, and thus our convolution is filling out the entire depth. But what about our filter size? So this is a one-dimensional data, and thus our filter size is just one-dimensional. So like if our filter size is 3, not like 3 by 3, and then our filter is like this, okay? And then if our filter size is 4 or 5, and then our filter size is defined as maybe like this, right? And then we can define our filters having this variable lengths, and 2 and 3 and 4 and so on. And then without using any paddings, we can obtain different activation maps. Different lengths of an activation maps. So so if our filter size is just 2, and then 1, 2, 3, 4, 5, 6, 7. So it has the length of 7, and then the activation map is having the length of 6, right? I mean, without allowing any paddings. If we use the filter size as 3, and then, yeah, we will have the size of 5, okay? Okay, and then we have all the different lengths of an activation map coming from each one-dimensional convolution filter, and then how we merge them is through like pooling over time. So pooling over time again. So in the case of pooling, we have a fixed size of a pooling window, right? But in this case, we actually have the variable size of a pooling window, and that pooling window size is actually the same as the activation map. So if our sequence length is 4, and then we just do the max pooling over all the 4 values, like if it was 1, -3, and 3, and 5, and then if we do the pooling, and then we will obtain a scalar value of 5, and then maybe this 5-dimensional vector was -3, 2, 1, -1, and 0, and then if we do the pooling and 2, right? And then we can just concatenate them into one single vector, and that vector is given to the next layer's output. Okay. So this is one example that kind of diversified our convolutional layer setting by having different size of different size of filter size, and even we use a different stride size within a single layer. Yeah. But anyways, so the time's up, and also yeah, the homework is due this Wednesday, and also since we have the Wednesday as a holiday, and then I will post some online lecture videos that I will record and upload, and then you should yeah, watch them and study them. Okay, thanks.
여기서요. I like 이게 여기 매핑이 돼 있는 거예요?
이게요.
아니
이걸
뭔지
내가-
몰라가지고.
네. 처음부터 이게 설명을 안 해줘서 그런데 이제 뭔가 이제 워드 인베딩이라는 기법을 배우면 각각의 이제 워드들마다 어떤 특정한 픽스드 디멘전의 벡터로 이렇게 나타내 줄 수가 있어요.
하나의 단어를 뭐 크기를 나타내는 거 같아요.
그러니까 그 단어의 뜻을 나타내는 어떤 벡터를 우리가 얻을 수 있어요. 그러니까 그게 없어갖고 좀 설명이 좀 주소가 없었을 텐데, 그러니까 우리한테 주어진 이 단어들 하나하나를 어떤 특정한 디멘전으로 이루어지는 벡터로 나타낼 수가 있어요.
아, 뭐 이 아이가 이
네, 맞아요.
요거고 라이기 요거고.
맞아요.
근데 그 필터들로 이 문장을 해석하는 거예요. 해석해서 이게 좋은 건지 안 좋은 건지. 성능이 있어요?
네?
성능이
아니 뭐 이거 많이 써요. 네.
아,
잘 되는 모델로 많이 써요.
네, 감사합니다.
얼마냐? 네.
컨버전 뉴럴넷으로 이제 배치 노멀리제이션을 안 해주는 경우에는 바이어스 값이 있어야 하나요? 근데 그러면은 필터마다 바이어스 값을 가져야 되냐, 아니면은 약간 생각해보면 그 이미지가 가지는 맨 처음 위치마다 바이어스가 있어야 되나요?
네. 일단은 바이어스는 이제 한 필터면 서로 다른 위치에 걸리든지 상관없이 바이어스는 다 동일한 바이어스가 매겨져요. 그러니까 어떻게 보면 이게 아까 3x3 필터면 3x3 필터를 맨 왼쪽에다 딱 해서 액티베이션 맵을 얻었고, 하나 옆으로 옮겨와서 또 액티베이션 맵을 얻었어요. 그럼 그 맵이 있잖아요. 거기다가 전체적으로 바이어스 값을 다 동일한 값을 모든 픽셀에 다 더해줘요.
동일한 값이 더해지는
네, 그게 일단은 컨볼루션 레이어의 컨볼루션 필터의 바이어스의 의미예요. 네, 그게 바이어스 의미고,
액티베이션 된 거에다가 더해지는 거예요.
네, 그 바이어스까지 추가가 된 게 우리가 부르는 액티베이션 맵이에요. 네, 그러니까 바이어스를 우리가 굳이 좀 이렇게 좀 마이너 해갖고 잘 생각을 안 하니까 그걸 좀 생략하는 경우들이 종종 있는데, 네.
근데 필터가 여러 개면 이제 여러 층이 쌓이게
네,
되잖아요.
그러면 그 필터마다 바이어스는 다 따로따로 있고요.
아, 필터마다 따로따로
네.
하시게 돼요. 그리고 오늘 마지막에 그 이제 문자열에서 그 CNN 그거 설명해 주셨었는데
네.
풀링 레이어 이거를 쓰게 되면은 그 CNN 같은 경우에 약간 공간적 특징 이런 게 사라져서 그 글자 분류할 때 안 좋잖아요. 근데 예시로 들어주신 거에서는
네, 맞아요. 그러니까 여기서 풀링을 해버리면은 여기서 스페셜 정보가 싹 다 사라지는 거거든요. 그러니까 이게 맥시멈 값이 어디서 나왔느냐에 대한 거는 뒤쪽 포워드 단에서는 전혀 몰라요. 네. 그러니까 이 패턴이 이 전체 문장 중에서 내가 이걸 하여튼 좀 두서없이 설명을 했는데 이게 그러니까 어느 위치에서 그 해당 맥스 액티베이션 값이 나왔는지를 몰라요. 네,
따로
뒤쪽으로.
몰라요.
네. 근데 그 정보는 어느 정도 잃어버린 채로 그냥 진행을 하는 거예요. 네. 근데 다만 이제 이 필터가 지금 이 필터 내에서의 위치 관계는 있잖아요. 그러니까 5개가 예를 들면 이게 여기서는 어떤 필터 패턴은 순서가 딱 이렇게 특정한 순서를 우리가 임포즈를 하는 거잖아요. 그러니까 그거 이 5개짜리로만 내가 일단은 보고 그것들 그 패턴이 어디서 나타났는지 모르지만 하여튼 그 패턴이 제일 세게 나타난 그 값 하나를 내보겠다라는 거거든요.
어쨌든 그 내가 찾으려는 가장 센 패턴 그것만 탐지해는
맞아요. 그 센 패턴이 어디서 나왔는지는 여기서는 잃어버리죠. 네.
그럼 이거에서는 약간 공간적인 건 없이도 배제하고 하는 거예요.
네, 약간은 그래요.
감사합니다.
요즘 제가 그 연답 신청해서 메일로 보냈었는데 확인을 아직 안 하신 거예요.
처음에 어떻게 되죠?
김도
Oh yeah, you told me that.
지금 끝나고 잠깐 이야기할 수 있어요?
하고 네.
네. 끝나고 좀.
예.
네.
Hey, so I was wondering, you talked about filters, and you talked about the shape of the filters, like the dimension of the filter. But what about the actual sort of what's inside of it in terms of you had like this filter with 111. You can also do like Sobel filter that detects edges, or a base filter that sort of blurs the image. Does that play into these things, or is that a separate discipline?
So you mentioned Sobel
Yeah,
filter?
Sobel, like the equivalent of like doing the gradient.
Like an
throughout
edge
the-
detector?
Yeah,
and things
exactly.
Like that. Yeah. So, yeah, they are exactly the same thing.
Okay,
So
you can
Sobel
use them like
Yeah.
specifically in a neural network
Right, but
as convolutional layers.
the main different thing is that in the case of a Sobel filter or in the case of traditional methods, we predefine our filter shape or filter coefficient, right? And then do the convolution operation as well, right? But in this case of like deep learning kind of style of a convolutional neural net, I mean the same operation is still there, but the filter is kind of learned from random initialization.
Okay. Okay. Okay.
So that's the main different thing.
Okay.
Yeah.
So would you? I've seen some people do pre-processing steps to images to sort of make them do different things, but that doesn't play into deep learning. That is sort of
Right,
inherent to like
Yeah,
the
yeah.
convolutional.
Right.
layers.
So that is called the end-to-end learning.
Okay.
So traditionally, most of the learning frameworks were not end-to-end because we predefine the filter shape, right? Like Sobel filters and any other kind of different, maybe SIFT or SURF or maybe Hawk features, and those are like the feature extraction is predefined by human, although really like genius kind of humans developed all these ideas, but those predefined feature or like feature extraction step may not be optimal for our own task,
Okay.
right?
Yeah.
So if
So you're saying basically like if I wanted to match a square, or I had different pictures of different like very sharp shapes or whatever, it would somehow learn something that would look like a Sobel filter in one of the
right.
convolutional layers.
Yeah. So for our own task, we may or may not need a Sobel filter.
Okay,
And,
but it is learned
instead-
and
yeah,
the
so
shape
it's,
is sort of a hidden hyperparameter.
Yeah,
you would
right.
say. Yeah, okay.
So all these feature extraction steps are self-learned through this backpropagation step. So this is called the end-to-end training, or this is a main kind of a reason for the huge success of deep learning, because all the human engineered feature extraction step may not be optimal for all the different, all the various kind of tasks that we.
Yeah. So you're saying that it would probably detect something resembling one of these filters or something like that, or would it be completely different? I'm just trying to wrap my head around what's actually, like how the filter shapes are being like trained towards something.
Right. So it's all learned by the backpropagation or through our data, right? So we just start with the random initialization. That's it.
Yeah. Okay.
Although we specified number of filters, in a particular convolution layers, but yeah.
Okay. That's a great answer. Thanks a lot.
선형대수학 수업 있잖아요. 저희 대학원에 하는 거. 근데 제가 그거를 수강 신청을 늦게 해서 마지막 날에 들어갔는데 다음 주에 휴강하시고 추석이고 이번 주도 개천절이라서 제가
또 휴강이고
수업을 지금 뭐 공부를 하려고 하는데 감이 안 와가지고 그 올려주신 비디오 보고 있으면 되나요?
네, 그러면 될 것 같고요. 네. 큰일이네요, 진짜.
네. 그래가지고 그냥 가만히 있으려니 좀 아는 게 없어가지고.
일단 뭐 진행되고 있었던 거는 크게 없어서. 네,
알겠습니다.
네, 뭐 필요하면 내가 공지를 보내거나 할게요.
네, 감사합니다.
그 과제를 제가 이번 주 수요일 과제인데 좀 아파가지고 첫 번째 그 튜토리얼도 못 냈거든요. 그 과제를 좀 늦게 내도 포인트를 받으시고.
네. 늦게라도 내면 좋을 것 같아요.
그 뭐 퍼센트까지 보시.
네, 그거를 적절한 선에서 이제 디덕트를 하려고 하는데.
네, 제가 그 전정신경 걸려가지고 근거리 작업하는데 어려움이 있어가지고 좀 천천히 하려고 그래서. 작년에도 듣다가 드랍했거든요.
네.
알겠습니다.
네, 그래요. 늦게라도 하여튼 뭐 제출하면 좋을 것 같아요. 네. 질문 있어요? 네.
이 뒷부분은 이해가 가는데 이게 그 거리 갖다 설명하실 때 그 부분만 이해가 좀 안 돼요.
네. 그거는 이렇게 많이 설명할 필요가 좀 없기도 했었던 것 같은데. 네. 그러니까 이거 결국은 이제 이너 프로덕트를 쓰면 컨볼루션 필터에서 결국은 이제 뭔가 밝은 색만 그렇죠. 이게 0으로 이제 이야기를 해서 그러는데 뭔가 이렇게 이렇게 해 놓으면 이제 딱 여기만 양수해야 되고 이제 여기만 이제 음수해야지 되잖아요. 네. 그러니까 뭐 무한정 이게 다 아까 질문한 것처럼 모두가 다 밝은 값으로 플러스 1이 되면은 액티베이션 값이 그렇다고 뭐 커지지는 않을 건데 근데 또 그럼에도 불구하고 이게 벡터 길이가 길면 길수록 사실 또 그 내적 값이 더 하여튼 그 내적 값이 절대 값이 더 커지기는 하잖아요. 그래서 사실 그 어떻게 보면 그 밝은 그 값 자체가 전체적으로 다 큰 리전이 이제 액티베이션 값도 더 큰 게 맞는데 근데 우리가 이제 이 컨볼루션을 이해를 할 때는 어떻게 보면 요 필터에 있는 요 특정한 요 모양 있잖아요. 요 모양이 제일 세게 나타난 고기에서 이렇게 딱 그 더더덜도 말고 딱 그 모양이 나타난 곳에서 이제 액티베이션이 제일 크게 나타나는 거로 이해를 하면은 크게 무리가 없다는
그냥 딱 그 정도.
이게 어떤 이유 아까 얘기했던 것처럼 뭐 벡터 길이가 길면 또 그거가 더 이렇게 패턴이 정확하게 매칭이 안 돼도 이제 그럴 수 있는데 뭐
이렇게 이해해도 되나요? 약간 그 필터랑 그 아까 그 예제 보여주신 것처럼 최대한 비슷하면은 이 벡터 했을 때 코사인 시뮬레이트가 그 코사인이 작으니까 값이 커져서 최대한 이게 비슷해서 그래서 맥스풀링을 쓰는 거라고 할까요?
아, 맥스풀링이요? 맥스풀링은 이게 내가 이게 좀 설명을 항상 하고 싶은 것보다 많이 못하는데, 이제 이 맥스풀링의 기본 아이디어는 이제 요 이제 2x2라는 요 지역 내에서
네.
그러니까 어떤 특정한 이제 액티베이션, 그러니까 특정한 이제 그 필터를 이렇게 적용을 해서 이러한 액티베이션이 나왔어요. 근데 이제 맥스풀링 2x2로 맥스풀링을 하면 이런 식으로 줄잖아요.
네.
그러면은 지금 이게 이미지가 어떻게 보면 이제 리사이즈 된 거로 생각할 수가 있거든요. 그랬는데 요 6이라는 값은 어떻게 보면은 이 여기에 2x2 리전에서, 그러니까 일단 이거를 이렇게 만들고 나면 사실 이 6이 요 4개 중에서 어디에서 정확하게 나타났는지는 우리가 정보는 잃어버리는 거잖아요.
네.
네. 근데 그게 그냥 뭐 괜찮다는 거예요. 네, 그게 왜 괜찮냐면 이게 내가 한글 강의를 좀 한 게 있는데, 이게 CS231N의 CNN 과정이 CNN이 또 이게 아주 이렇게 좀 로우 레벨에서의 좀 직관적인 그건 조금 약한 측면도 좀 있고 한데, 이게 또 너무 베이직한 거라 내가 또 설명을 또 그걸 또 시끄럽게 하자니 좀 그래갖고 안 하긴 했는데, 지금 보면 이 X자를 디텍트를 하고 싶은데 지금 우리가 갖고 있는 X 패턴이 이런 거예요. 그러니까 이게 지금 보면 약간 회전이 된 거잖아요.
네.
그리고 여기서 보자. 회전뿐만 아니라 이게 크기가 좀 작아질 수도 있고 그런 건 없나? 네, 그래요. 하여튼 이게 약간씩은 또 좀 다른 점이 있음에도 불구하고 우리는 큰 틀에서는 이거는 X라고 봐야 되는 거잖아요.
네.
그러니까 역시 마찬가지로 이제 뭐 고양이든 강아지든 뭐 그것도 어떤 특정한 딱 그 포지션의 어떤, 그러니까 여기가 뭐 딱 요렇게 생긴 것만이 아니라 얼굴이 좀 이렇게 들려 있을 수도 있고 뭐 약간 이런 거잖아요.
네.
그러니까 이게 우리가 찾고자 하는 패턴이 뭐 어딘가 저 위치에 나타난 거는 우리가 알겠는데, 그거는 이제 잡아냈는데, 근데 이제 뒤쪽에서 판단을 하기에는 이거를 조금씩 더 하이 레벨에서의 어떤 우리가 판단을 얻어내기 위해서는, 그러니까 좀 그걸 하기 위해서는 그런 어떤 스페이셜 레졸루션 자체를 우리가 의도적으로 버리는 게 뒤쪽에서 도움이 될 수 있다는 거예요.
약간 오차도 인정하려고.
네, 맞아요. 그런 오차를 인정하기 위해서 그렇거든요. 네, 그래서 이게 이제 이렇게 하는 맥스풀링의 어떤 기본 아이디어가 좀 약간 그런 거예요. 어디에서 이 4개 중에서 어디에서 요 맥스 값이 나타났는지 그 정보는 잃어버리되, 그게 잃어버려서 꼭 안 좋은 거냐? 그게 아니라 그게 오히려 뒤쪽에서 뭔가 큰 틀에서 뭔가 하이 레벨에서 판단을 하기에는 더 좋을 수 있다. 네. 그리고 아까 질문 중에 이제 이거에서 뭐 에버리지 풀링이 왜 맥스 풀링이 왜 에버리지 풀링보다 좋으냐 뭐 이런 얘기도 있고 했는데, 뭐 그런 얘기가 이제 강의에 나왔는데, 이제 에버리지 풀링을 하면 이게 이제 5, 6, 1, 2를 다 이제 평균을 내는 거거든요. 근데 예를 들면 이게 우리가 찾고자 하는 어떤 특정한 에지가 뭐 이렇게 사선으로 어떤 왼쪽 위에서 오른쪽 아래로 내려가는 이 사선이 이 4개의 위치 중에 여기는 그렇게 세지 않았는데 여기 조금 세고 여기는 진짜 세고, 예를 들면 그러면 그 사선이 이 4개의 위치 중에서 그래도 세게 나타나는 어떤 특정한 지점은 여기이고, 그리고 그 값이 6인 거잖아요.
네.
그 정보를 전달해 주는 게, 이 4개를 다 평균을 내면 여기에 그래도 센 6이라는 값이 나왔음에도 불구하고
약간 전체적으로 이렇게
흐려진다는 거죠. 네. 그래서 여기에서 어떤 그 6이 그래도 어떤 요 지점에서는 그 패턴이 6만큼의 세기로 나타난 부분이 분명히 있었음에도 불구하고 이걸 그냥 평균을 내면 이제 이 정보가 그냥 좀 스머시 된다는, 좀 이렇게 된다는 약간 그런 의도에서 이거를 맥스풀링을 쓰는 거거든요. 네.
그 마지막으로 아까 랭스가 길면은 언페어 해가지고 원래 값을 맞춰주는데 어차피 백프롭에서 맞춰주니까 상관없다고 했잖아요. 근데 만약에 랭스를 안 맞추고 하면은 그럼 그대로 웨이트이 그냥 그쪽이 센 걸로 시작을 해서 맞춰주는 건데, 그럼 애초에 그냥 시작할 때 랭스를 맞추고 하면 좀 더 빠르게.
근데 그 랭스를 이제 맞춰주는 거는 이제 이미지상에서 이제 겹치는 리전도 있고 하니까
네.
이거를 맞춰주기는 좀 어려워요. 그렇잖아요.
네네네.
네.
그 이미지에서 그거 안 쓰는.
그러니까 이 필터를 아까 여기서 여기 갖다 대고 여기 갖다 대고 이렇게 할 때 그 각각을 그 각각을 일단 맞춰주고 한다고요.
네.
그러면 그게 이제 코사인 시밀러리티랑 이제 같아지거든요.
네.
근데 이제 그렇게 이제 안 한다는 거죠. 그러니까 좀 불완전한데 이제 그거를 그렇게는 하지 않아요. 네. 그게 이게 좀 그게 평균이 그러니까 평균적으로 걔네들이 길이가 다 똑같은 게 그게 좀 잘 생각을 해보면 그게 이론적으로 좀 증명이 대충 가능하거든요. 그게 무슨 말이냐면 예를 들면 여기 왼쪽 위가 되게 밝고 어디는 되게 어두워요. 근데 우리가 그러면은 보통 이 이미지를 우리가 처음에 이제 뉴럴넷을 쓸 때 이제 처음에 입력으로 넣어줄 때 이거를 이제 mean normalization을 하거든요. 그러니까 그 평균 값을 이렇게 빼줘요.
네.
그러니까 이제 0에서 255라는 RGB 어떤 특정 채널의 값을 0에서 255라고 한다면 이 값이 이제 마이너스 128에서 뭐 127로 이렇게 옮겨 오거든요. 레인지가. 그럼 일단 인풋 값은 이제 대충 마이너스 1에서 1 사이로 대충 한다고 보면 그러면 이제 어떤 지역은 이제 양수고 어떤 지역은 mostly 음수고 이렇겠죠. 그렇죠? 근데 중요한 건 우리 필터의 코에피션트는 어떠냐 하면 3x3 여기 딱 이렇게 되면 3x3 필터의 어떤 값들은 걔네들은 이제 우리가 일반적으로 평균이 다 0인 both positive and negative 값들이에요. 그러니까 이게 필터 안에서는 코에피션트가 꼭 양수만 있는 게 아니라 이제 양수와 음수가 적절히 섞여 있는 거죠. 그러면 여기서 이제 밝았던 리전이라 하더라도 우리가 이 포지티브 및 네거티브 값들로 이렇게 이렇게 믹스가 되어 있는 그런 컨볼루션 필터를 딱 대면 얘네들의 내적 값은 대략 0에 가까운 값이 나와요.
네.
그리고 또 어디는 또 0, 마이너스와 플러스가 적절히 섞여 있어서 이 필터를 또 이렇게 갖다 대면 그럼 얘네들도 뭐 마이너스 플러스가 막 지네들이 뒤섞이면서 대충 0 근처의 값들이 나와요. 그러니까 벌써 첫 번째 컨볼루션 레이어만 싹 지나면 이제 그 밝았던 리전이 더 이상은 그 아웃풋 액티베이션 값이 더 이상 그렇게 밝았던 리전이 이제 밝은 값으로 이렇게 유지가 되고 그러질 못해요. 그러면 이제 대부분의 리전에서의 어떤 값들은 대략적으로는 평균적으로 이제 0 근처에 이제 액티베이션 값을 가질
네.
거고 그러다 보니 이제 얘네들이 이제 길이들이 대충 다 비슷하다라고 볼 수 있는 거죠. 네.
감사합니다.
이런 데까지 설명을 해야지 사실 아까 그게 좀 완벽해지는데 하다 말아갖고 좀 괜히 혼란만 준 게 아닌가 싶은데. 네.
감사합니다.
네.
혹시 샤비에르 여기 따로 좀 다루시나요?
네?
샤비에르 이거.
합의의 이니셜라이제이션. 네, 그것도 해야죠. 그것도 해야죠.
그때 듣겠습니다.
그것도 근데 대충 마찬가지인데
네.
합의의 해 이니셜라이제이션이 그게 이제 뭐냐면 아나요 대충?
네, 좀 찾아와가지고
네.
좀 맞춰줘가지고.
네.
네.
그러니까 분산이다 1짜리가 노드가 3개가 합쳐지면 분산이 3이 되거든요.
네.
그래서 이제 개값이 이제 분산이 역시 1이 되도록 맞춰주기 위해서 그 팬인으로 이렇게 루트 해갖고 나눠주고 그거거든요. 해는 그게 이제 렐로를 거치니까 이제 반으로 뚝 잘리니까 이제 저기 루트 이만큼을 더 곱해주면.
네.
그거 두 개는 되게 기본적으로 쓰는 거예요. 그냥 하면 돼요. 이니셜라이제이션 펑션 콜 해갖고
네.
해니 합의해니 뭐 이거 쓰면 돼요.